In the field of science and huge mysteries, the subject of what existed previously to the gigantic explosion has sparked mixed conversations and fascinated characters for quite a while. This huge question doesn't just test how we could decode the universe, it poses a challenge to the genuine furthest limits of human knowledge. Imagine standing at the edge of existence, examining the colossus, observing and pondering the contents that existed before our universe was imagined. The event of the Big Bang marked the beginning of time, space, and all that we know. Anyway, was there a second earlier? In the past, this might have been a condition of nothingness, a calm before the cosmic gathering started. And if this is true, was it, or perhaps, was there something far more frightening that existed before the beginning of time? As we continue with this inquiry, science takes us on a journey past the universe's beginning point into thoughts that challenge our consciousness. Physicist Brian Cox, well known for his investigation into the wonder of the universe, suggests that something surprising may have existed prior to the enormous detonation. He moves us to reconsider our ideas of reality and existence. In this investigation, we dissect the theories, the research, and the dazzling insider information that could figure out what happened before everything else. We'll explore thoughts like self-importance and growth, quantum changes, dark energy, and even multiverse. The responses we found may just paralyze you, yet they could likewise open up new perspectives on our position in the universe. Get ready to dive deep into a world beyond imagination and science, in the midst of the obscure, around the shadows, leaving scientists shocked, and sometimes even upset. We ought to explore what existed before the Big Bang and why these theories test everything we thought we knew. To appreciate what may have existed before the Big Bang, we first need to painstakingly analyze what the Big Bang truly was. The Big Bang, as scientists define it, means the point in time when the universe became extremely hot and dense, rapidly expanding to cause the development of all matter and energy. When we look at the night sky, there are no boundaries. It reveals evidence of this hot beginning, with the expansion of galaxies moving this way and that from an early starting point. However, why did this happen? Furthermore, was there a period before this dense, hot start? As indicated by the idea of massive expansion, there was, without a doubt, a time before. Furthermore, it lacked any semblance of void or peacefulness. Vast expansion suggests that before the Big Bang, the universe was in a state that was cold, vacant, and loose, essentially like an immense vacuum. Anyway, this vacuum wasn't entirely unfulfilled. It contained a tremendous amount of energy that fueled the quick extension of space itself. This is called inflation. Inflation occurred so quickly that it essentially established the foundation for the future of everything, a part of a subsequent space extending at unfathomable rates. Until the extension slowed down, transforming the energy into matter, particles, and the forces we see as the Big Bang. But what was the nature or purpose of this energy? Why did it suddenly grow the universe, and why did it stop? Experts believe that this immense expansion resulted in patches of the universe, each experiencing its own evolution. Imagine a fabric expanding after the Big Bang, endlessly, with tiny pockets of air forming, each one representing a universe, including our own. This idea, called inflationary multiverse, suggests that there are conceivably endless Big Bangs and an infinite number of universes. Our own is just one of many. This huge, mind-bending reality challenges our perception of the entire universe, leaving us with the question, what else is there? The idea of nothingness before the Big Bang is speculative, not real, at least according to our current understanding. Regardless of whether you eliminate all energy, particles, and radiation from the universe, it would still not be genuinely void. Our universe is filled with dark matter, dark energy, quantum fields, and other forces that weave an inevitable artwork, embroidered with something, even in its most empty state. Even if we imagine stripping away all of these forces, leaving a dead space, the universe would still produce new species of energy. This reality alone is bewildering to specialists, as it suggests that actual inertia could be impossible in our infinite universe. Space itself has properties, rules, and constants that keep it from being completely empty. Imagine creating a region with literally no particles, no radiation, and no energy, except quantum fields and important constants. These would continue to exist, suggesting that this nothingness has properties. For instance, there's a peculiarity called zero-point energy, which represents the least possible energy condition of quantum fields. In this state, particles are still able to temporarily appear and vanish, creating an unsettling resonance of movement, even in what should be empty space. This challenges our idea of a real void and suggests that, indeed, prior to the Big Bang, there was something scientists are only beginning to understand. One of the most amazing cosmological theories currently in use is the possibility of timeless expansion. Inflation could cause our universe to exist forever. Brian Cox describes an astonishingly vast inflationary multiverse where universes are infinitely created and continue expanding. Imagine each Big Bang as if lit by a flash in another universe. Despite the fact that inflation continues, it creates countless other universes. In theory, this cycle could continue for eternity. This idea of vast universes gives birth to an enchanting concept of a fractal universe, where each new universe may develop its own Big Bang. Every universe exists as a separate, independent domain, unaffected by the others, as a result of the rapid growth of space. This hypothesis provides researchers with something both exciting and upsetting: the suggestion of a multiverse that never ends, with no predetermined beginning or end. Our universe may be just one speck in a giant cosmic structure, forever expanding and continuously constructing new universes. And what if the disturbing reality is that there is no before or after, but rather a timeless pattern of universes forming and decaying? Our interpretation of nothingness changes when we look at the theory of quantum fields. According to this theory, the universe is not just an assortment of matter floating in space. Rather, it's a complex network of energy fields that fills the universe, connecting to create everything we observe. These fields resemble invisible seas, made up of particles that act as disturbances or waves. Even when these fields are at their lowest known level of energy, called the vacuum state, they are still alive. Particles can form and vanish in these fields, momentarily acquiring energy before returning it. This phenomenon generates virtual particles, substances that immediately exist and then vanish, leaving only a faint memory. Because of their presence, the idea of virtual particles challenges the idea of a real void. Imagine a universe where nothing exists: no matter, no radiation, no energy. Would you have total nothingness? According to quantum field theory, you wouldn't. Even in a vacuum, fields would remain active, sometimes creating transient particles. This idea, that the universe has no true origin but instead undergoes infinite rebirths, leads us into one of the most profound realizations in cosmology: perhaps the concept of beginning is flawed. Maybe our language, our tools, and even our minds are too limited to grasp the full scope of reality beyond time and space. What if existence itself is timeless? Physicists and cosmologists are beginning to embrace theories that challenge even the most basic assumptions about the universe. String theory, for example, suggests that all matter is composed of tiny vibrating strings, existing not just in 3 dimensions, but in up to 11. If true, our universe could be a brane, short for membrane, floating in a higher dimensional space. Other brands could be drifting parallel to ours, sometimes colliding, triggering events like the Big Bang. This theory, the ekpyrotic model, proposes that our universe was born from a collision between such brands. The Big Bang wasn't the beginning, but just a moment in a much larger cosmic cycle. The universe, in this view, could oscillate not just within itself, but through interactions with parallel realms, creating shockwaves of creation and collapse. And then, there's another, stranger thought: that time itself is emergent, not fundamental. According to some physicists, time may not be a fixed backdrop against which events unfold, but rather a property that arises from the entanglement of particles and the expansion of entropy. If that's the case, then before the Big Bang is a meaningless phrase, like asking what's north of the North Pole. In this strange new view, the universe isn't a story with a beginning, middle, and end, but more like a mathematical structure that simply is, a block of space-time containing everything that ever was and will be, all existing at once. Past, present, and future could be illusions born from our limited perspective as time-bound creatures. And yet, even as these ideas stretch the limits of understanding, one thing becomes clear: we are only at the very beginning of this journey. What came before the Big Bang? We may never have a final answer. But the pursuit of that answer, the questioning, the curiosity, the science, the wonder, is perhaps even more valuable. It shows us that reality is bigger, stranger, and more beautiful than we can possibly imagine. We look up at the stars not just to understand where we came from, but to confront the infinite and ask, again and again, what lies beyond? Waves are another intriguing idea that could hold clues to what existed before. The gravitational waves from the Big Bang are ripples in space-time brought about by massive cosmic events. Scientists believe that if early-stage waves are ever found, they could reveal new understandings of the universe's earliest moments. These waves could serve as the echoes of the Big Bang before it occurred. Should they be identified, they might provide proof of the universe's previous states. The potential discovery of gravitational waves in their early stages is one of the most intriguing possibilities in cosmology today. It might not only reveal the truth about the Big Bang but also offer a glimpse into the cosmic state before our universe was created. This theory provides an enticing prospect, locating gravitational waves that could serve as fingerprints of a pre-Big Bang universe. As we keep looking into what might have existed before the Big Bang, we delve into concepts that push the boundaries of our understanding, even challenging our most fundamental assumptions about space, time, and existence itself. One of the most amazing concepts originates from the realm of quantum gravity, which aims to merge quantum mechanics with general relativity. This merger could potentially reveal a unified theory of everything and provide insight into what existed before the Big Bang. Quantum gravity suggests that space and time are not smooth, continuous entities as we experience them, but instead are discrete, granular structures. According to this theory, the space-time fabric itself could have been formed from a microscopic, Planck-scale structure with tiny quantum changes that shape the universe in ways we cannot yet fully comprehend. What we perceive as the smooth continuum of space and time might have only emerged from these changing quantum fields. As a result, the reality before the Big Bang could be described by a radically different concept, one where space and time themselves were not fully formed. Another possibility is that the universe is part of a vast cosmic landscape of possible universes, each with different physical laws and constants. This theory, known as the string landscape, arises from string theory, which suggests that all fundamental particles are actually tiny strings that vibrate. Within this framework, there are many possible configurations of these strings, each corresponding to a different set of physical laws. The string landscape could imply that our universe is just one of many, each emerging from a distinct Big Bang-like event. The existence of such a landscape also suggests that other universes might have different dimensions, different strengths of gravity, or even various forms of matter. In this perspective, our universe might not be unique but rather part of a multiverse, a collection of universes, each evolving independently. The multiverse theory offers a hypothetical yet intriguing response to the question of what came before the Big Bang, another universe in a different configuration, possibly leading to endless cycles of creation and destruction, with no definitive origin. In addition to these cosmological models, some theoretical physicists have also considered the role of black holes in shaping the nature of the universe, a hypothesis gaining traction. The idea is that our universe may be the result of the formation of a black hole in another universe. In this scenario, the singularity at the center of a black hole could serve as a gateway to another universe, with the Big Bang being the moment when such a black hole gave birth to our cosmos. This hypothesis is supported by the fact that, according to general relativity, the singularity at the center of a black hole is a point where space and time curve infinitely, creating a region where the known laws of physics break down. It's possible that the extreme conditions inside black holes could lead to the creation of new universes. This may suggest that what we consider the Big Bang was merely the birth from the singularity of an ancient black hole. Exploring these concepts requires a deep dive into the very nature of time itself. Some cosmologists speculate that time, as we understand it, may have had no meaning prior to the Big Bang. Assuming that the Big Bang marks the beginning, there may have been no before in any standard sense. This point of view suggests that time itself might have emerged from a quantum fluctuation or from an initial state in which the usual distinctions between past, present, and future did not exist. This would lead us to reconsider the idea of causality, which relies on the assumption that events take place in a straight line. If time did not exist in the way we experience it, then the question of what preceded the Big Bang becomes nonsensical, as there would be no temporal framework to support it. Complicating the picture further are theories of cyclic time. As mentioned previously, cyclic cosmology suggests that the universe undergoes endless cycles of birth, development, and eventual demise. In this model, the Big Bang could symbolize merely the most recent swing in an eternal series of universe cycles. These cycles might not be identical but could evolve in different directions, each with unique physical properties. The cycle of the universe, according to this theory, would be a continual process with no true beginning or end, rendering the question of what arose prior to the Big Bang, in the conventional sense, meaningless. The idea that time itself might be cyclical suggests that every Big Bang could be followed by a contraction and reinitiation, an endless loop. Another avenue of investigation into the nature of the cosmos is the potential of a primordial liquid of bits and fields that existed before the universe's rapid expansion. This idea suggests that before the universe began to expand rapidly, it was filled with a dense and hot mixture of fundamental particles such as quarks, bosons, and leptons, all in a state of extreme energy. These particles would have been interacting at extremely high temperatures and densities, laying the foundation for the formation of matter and energy. As the universe cooled, some versions of this theory suggest that this primordial soup existed in a quantum foam, where particles constantly emerged and vanished as a result of quantum uncertainty. The properties of this soup could potentially offer insights into the earliest moments of the universe, and, by extension, what preceded the Big Bang itself. In the end, what came before the Big Bang remains one of the most profound mysteries in science. As our knowledge of quantum mechanics, cosmology, and fundamental physics expands, new hypotheses will continue to emerge, offering increasingly complex and sometimes paradoxical explanations for the origins of the universe, a universe we might never fully comprehend. Yet, the pursuit of this knowledge will continue to stretch the limits of human curiosity, driving us to explore the unknown and the boundaries of existence. The further we peer into the origins of our universe, the more we come to understand that the question itself, what came before the Big Bang, might require an entirely new framework of thinking. As we develop more sensitive instruments and refine our mathematical models, we may find that the answers are not found in what came before, but rather in the nature of beginnings themselves. Some physicists argue that the universe did not arise from nothing in the traditional sense but from a state of quantum potential, a timeless, formless realm governed not by classical physics, but by the strange rules of quantum probability. In this interpretation, the universe could have emerged from a vacuum fluctuation, where the uncertainty principle allows for energy to spontaneously appear, leading to the formation of space, time, and matter. Others propose that the universe is a holographic projection. What we perceive as three-dimensional reality might actually be encoded on a distant two-dimensional boundary. This radical concept, rooted in string theory and black hole thermodynamics, suggests that all of the information about our universe is written on this boundary, blurring the lines between what is real and what is illusion. Then there are those who consider the possibility that our universe is a simulation, an elaborate construct running within an advanced intelligence's computational system. Though speculative, this idea has gained surprising traction in philosophical and scientific circles, not because of empirical evidence, but due to the mathematical elegance and computational nature of the universe itself. The digital patterns we see in physics might not be just convenient descriptions, they might be the code. All of these ideas, while vastly different in their assumptions, share one thing in common. They challenge our very definitions of time, space, and causality. The more we learn, the more we are reminded that the universe is not only stranger than we imagine, it may be stranger than we can imagine. In seeking answers, we confront paradoxes that seem unsolvable, yet through these contradictions, new insights often emerge. The journey is as important as the destination, for with every theory, experiment, and observation, we refine our understanding, not only of the universe, but of our place within it. As we stand on the edge of the known and gaze into the vast unknown, we do so with a growing awareness that the origins of everything we see, feel, and experience may lie beyond the reach of time itself. And yet, we look anyway.